Hi, my name is Adam Corrao, and the work I'm showing today is an overview of our ongoing efforts to better determine the size and shape of nanoparticles using synchrotron X-ray diffraction. It's well known that particle morphology has a large impact on performance in catalysis and energy storage, but the implications for material synthesis are less clear. As a synthesis center, we're interested in understanding why different synthesis conditions lead to a specific morphology and how we can use that knowledge to tailor synthesis. In order to understand the role of particle morphology and its evolution during synthesis, we need robust, bulk analytical approaches. Powder diffraction is well suited for this problem since peak shapes give us insight to crystallite size and lattice strain, and in situ measurements allow us to track morphological changes during synthesis. However, existing peak shape fitting approaches typically use isotropic models where size and strain vary as a function of scattering angle, but these often are insufficient for describing nanoparticles' microstructure. To address this, we've developed a peak shape fitting approach in which peak intensities are constrained by a structural model and peak shapes are independently refined. This allows us to assess both anisotropic size and anisotropic strain broadening without the need for an explicit model of broadening or particle shapes. In the three cases shown here, we demonstrate the utility of this approach and the details learned that would have otherwise been inaccessible. In the first panel, we show work done in collaboration with UCSD to quantify the phase fractions of hexagonal close-packed and cubic close-packed cobalt polymorphs despite the presence of anisotropic particle shapes and stacking faults that lead to complex peak broadening. The second panel shows ongoing work to understand the evolution of polymorphism in nanoporous cobalt and what we've learned so far about the HCP to CCP phase transformation. Our ex situ and in situ temperature studies suggest that there's a particle size dependence for the transformation and that the onset temperature is variable. In the last panel, we show the application of this independent peak shape refinement approach for following the evolution of particle anisotropy. Here, we used anisotropic fits to Williamson-Hall plots to deconvolute size and strain broadening and successfully determined particle shapes. The fitting approach used in these three cases is generalizable, and we're working to both build a more user-friendly interface and extend the models for routine use. Please let me know if you have any questions or are interested in applying this approach to your own challenging data.